If you have things moving in the same direction, like an angry sheep chasing a lion, or maybe things moving in exactly opposite direction, like these guys approaching each other, in such cases, we can calculate the relative velocity between them just by subtracting them with signs. And we have covered this in earlier videos in one-dimensional motion. And if you have not seen them or you need a refresher, then please go back and watch those videos and then come back over here. Because in these videos, we're gonna talk about relative velocities between things that are moving at some angle with respect to each other. So let's take an example. So imagine we have a situation where a sheep and a lion are moving perpendicular to each other on streets. Yeah, they're animals running on the street. What we would be interested now is in calculating the relative velocities in this example. Like for example, what is the velocity of the sheep as seen by the lion from the lion's perspective? What would that be, and how do we even calculate that? Could we just like directly subtract? Can we do that? Well, let's see. What we can do is we can use the same concept that we did before. The concept was this: if you want to calculate from velocity of the sheep from lion's perspective, then we have to look at things from lion's perspective. The first thing is the lion does not see itself moving. As far as the lion is concerned, it's at rest. And this is familiar. And when you're jogging, you don't see yourself moving, right? Instead, you would see the rest of the world going backwards. Similarly over here, lion would consider itself to be at rest, and the whole world, including this road, would be going backwards at 3 meters per second. All right, so let's just look at what that looks like. So here it is. Let's jump into the lion's reference frame or lion's perspective, and from the lion's perspective, you would see the whole road going backwards this way. And if you have used GPS, then you see something very similar, right? You don't see yourself moving, you see the rest of the world moving. Now comes the big question. What will the lion see the sheep doing? I mean, think about it. The sheep is moving 4 meters per second on the road, on the ground, but the ground itself is traveling backwards 3 meters per second. So to figure out the relative velocity of the sheep, seen from the lion's point of view, we will wait for 1 second and figure out where sheep ends up. All right, let's do that. So in 1 second, we would see that the sheep would have traveled 4 meters on the ground. All right, so let's just write that down. On the ground, the sheep would have traveled 4 meters. Here it is, 4 meters on the ground per second. But in that 1 second, you would also see that the road and the sheep would have gone downwards 3 meters. Okay, so let's put that in as well. So the road and the whole ground, whole ground goes 3 meters in 1 second. So now here comes the big question. How much did the sheep move? Well, notice the sheep was initially over here, but now it's over here. So if you look from the lion's point of view, the sheep has moved in this direction, this way. So this means that the sheep is no longer traveling towards the right. Instead, the lion would see the sheep moving this way, this direction. That is the direction of the velocity of the sheep. And at first it might sound a little weird as to, why would the sheep be doing that? But let's play an animation to really convince you that that's really what's happening. So here it is. Here's the perspective of lion. All right. This is not very convincing, isn't it? Okay, let's look at it one more time. This time we will see some ghost images. You can clearly see now that the sheep is indeed moving at an angle, isn't it? So watch it over and over again until you really get convinced about this. All right. Okay, now the next thing would be to calculate this. How much is this distance? Well, this is a right angle triangle. And in right angle triangle, we can use the Pythagoras theorem. This is our hypotenuse. So we could say the hypotenuse squared. The Pythagoras theorem says the hypotenuse squared is equal to the sum of the squares of the other two sides. So that should be equal to the 4 squared plus 3 squared. And that gives us 16 plus 9, which is 25. Or the hypotenuse turns out to be square root of 25 which is just 5, which means this length is 5 meters, and this happened in 1 second, right? So we could say it's 5 meters per second. This means that the lion sees the sheep traveling 5 meters this way in 1 second. In other words, the relative velocity of the sheep, as seen from the lion's perspective, is 5 meters per second this way. Alright, now since we're talking about velocity, it's not just the magnitude, we also want to calculate the direction. I mean, no, we understand the direction is this way, but what exactly is this direction? So we can answer that by calculating the angle. So let's calculate this angle, for example. How much is this angle? So we can use trigonometry. We can use sine, cos. We usually prefer to use tan. It's not a necessity. You can use anything you want. But if I use tan, we will get the opposite side. 3, oops, let's put the proper colors. 3 divided by 4. That makes theta equals tan inverse of 3 divided by 4. And there we have it. So if someone asks you now what's the relative velocity of the sheep as seen by the lion, we could just say it's 5 meters per second at an angle of tan inverse of 3 by 4 with the horizontal or something like that. Alright, now let's put the whole thing, this whole result, in terms of symbols. Okay, remember how we used to write symbols for relative velocity? Well, we are calculating velocity of the sheep with respect to lion, right? So we would write it as velocity of the sheep with respect to the lion. The only thing we have to do now is make sure that we put vector signs, because we're looking at things in 2 dimensions, right? So we have to use vectors. And if you're not familiar with vectors, or if you're uncomfortable with vectors, then it would be better if you could first watch those videos on vectors and then come back over here. So anyways, let's try to write this now. What is this equal to? This vector is this vector which we have drawn, 5 meters per second. So how did we get this is the question. Well, we added this vector and this vector, right? This is a triangle law, vector addition. So we have to add the white vector, but white vector is just the velocity of the sheep as seen from the ground. So that is equal to velocity of the sheep as seen from the ground plus, because we are adding, this vector. What is this green one? Ooh, that's the negative of this vector, right? I mean, since the line is going upwards 3 meters per second, that's the reason the ground goes backwards 3 meters per second from the line's point of view, right? So this would be the negative of the velocity of the lion as seen from the ground. And there we have it. This is a general result. Just to make it more concise, we have a plus of a minus. We will rewrite this. We'll rewrite this as velocity of the sheep with respect to the lion as velocity of the sheep minus velocity of the lion, right? And this is the same as this, okay? And the reason I want to box this expression is because this is very similar to what we got in 1 dimension. Do you remember in 1 dimension we got VAB equal to VA minus VB? Well, guess what? We got the exact same result. V of SL equals VS minus VL. The only difference here is that we have to subtract vectorially using the triangle law or the parallelogram law. And in fact, even in 1D, we do the same thing. The only difference is over there, we just use signs to take care of directions. That's it. But it's exactly the same thing. And so this is how, in general, you can figure out relative velocity between things, even when they're not moving in the same direction.